Hello everyone, my name is Anki Tang. So in this video, I will walk you through the key techniques that I use to improve the performance of my loan default classifier. So me and Shelun Zhou will explain how we enhance the feature engineering and handle the class imbalance and selected the best model and find the turned hyperparameters to maximize the F1 scores. And additionally, I will discuss how I validated and accessed the model's fit to ensure it generalized well. So the first one is to improve the classifier's performance. So in order to improve the performance of the classifier, we apply the several techniques. So firstly, I implement the feature engineering by creating the meaningful financial indicators such as the debt to income ratio, which measures an applicant's financial burdens, and the credit history length to age ratios, which reflects the credit experience, and the loan interest burden, which accounts for the true cost of the loans. So these features provided the deeper insights into loan applicants' financial stability and help to the models better distinguish between the high risk and low risk um, borrowers. And next, I will tackle the class imbalance. That's a common issue in loan default prediction, where non-default cases significantly outnumber defaults. So to address this, I applied uh, uh, CMOD um, to generate the synthetic samples for the minorities class and ensuring that a balanced dataset. In addition, I adjusted a class weights in models like logistic regression and random forest to prevent the model from being biased towards the non-default cases. So to find the best performance model, I compared the three classifiers. The first one is for the logistic regression, which is simple and interpretable, but struggles with complex relationships. And the second one is for the random forest, which performs well but can overfit. And the third one is for the XGBoost, which shows the highest F1 scores due to its availability to capture non-linear relationships and rank features importance effectively. So after testing and comparing these models, we can see that XGBoost outperforms the others and make it the best choice for the final classifier. And so to ensure the model generalize well, we implemented the stratified k-fold cross-validation rather than using a simple trend test split. This approach allowed the model to be tested on multiple datasets partitions and reducing the variance and improve the reliability. And we also analyze the learning curves to check for the overfitting or underfitting. So a significant gap between training and validation performance indicates overfitting, which I mitigated by turning hyperparameters like max depth and learning rate and the number of estimators in XGBoost. So if both training and validation performance were low, it suggested the underfitting, which I addressed it by adding more meaningful features. And finally, we evaluated the model using the confusion matrix and also the precision recall curve using an assess trade-off between the false positive and also the false negative. So in the loan approval scenario, like for the false positive, it shows that it's approved risky applicants that can lead to the financial losses, and for the false negatives, that is rejecting good applicants results in lost for the business opportunities. And to balance this risk, I adjusted these decision thresholds and optimization the models to minimize the financial loss while maintaining the business profitability. And combining these features engineering, class balancing, and also the cross validation and the model tuning, I was able to significantly improve the classifier's performance and also ensuring it's both accurate and also well fitted for the real world law and approval scenarios.
And now we focus on the size and the improvement about the model. To ensure the model's reliability and robustness, we implement the stratified k-fold across validation, which ensures balanced class distribution across training and validation sites, preventing overfitting and improve generalization. The model comparison include logistic regression, random forest, and XGBoost, with the XGBoost achieving the highest cross-validated F1 score of 0.9476 plus or minus 0.002. Additionally, I conducted a learning curve analysis to diagnose overfitting and underfitting. If training accuracy was high, but validation accuracy was low, it indicated overfitting, whereas low accuracy in both suggested underfitting. By fine-tuning hyperparameter, we optimize the model for balanced fit. And next, we focus on implement with confusion matrix and precision recall curve. To ensure optimal model performance, we analyze the confusion matrix and the precision recall curve, focusing on the trade-off between false positive and false negative. A high false positive rate could lead to financial loss by approving risky loans, while a high financial negative rate might result in missed business opportunities by rejecting good applicants. By fine-tuning the classification threshold, I balanced this risk to improve decision-making. For future improvement, integrating external financial data such as macroeconomics trend and credit bureau reports would enhance credit worthiness, assessment, and model accuracy. Additionally, implementing real-time monitoring for data drift and automated model training would ensure the model adapts to changing economic conditions, maintaining its predictive power and long-term reliability in production. In summary, we improve the classifier use feature engineering, class balancing, and cross-validation. The XGBoost model performed the best, and we validate its reliability using learning curves and precision recall analysis. Future improvements could include external data integration and real-time monitoring. This is our projects and our presentation. Thank you for watching and listening.